At this moment, we study about the properties of a Fourier transform. Fourier transform is defined in this integral, and the inverse Fourier transform can be taken in these integrations. And we already studied the Fourier transform satisfy the linearity properties. And when we shifting time, it affecting to the spectral domain as a phase in this way. Keep in mind the magnitude of this phase change is always unity. If taking magnitude of this one is always 1. So it means time domain shift doesn't change the magnitude of the spectral domain, but it changes some phase of the spectral domain. The third one is a time and frequency scaling. Here is a time scaling factor applied here. Then by taking the Fourier transform, we can prove that it is 1 over absolute value of A, and the spectral domain is divided by A. By use of this functional property, if A is larger than 1, in time domain it shrink. If A is larger than 1, shrink in I think about it, this one is better. Magnitude of A is larger than 1, function will shrink. But what about the spectral domain? It's expand. In the spectral domain, the opposite is the same. If expanding in the time domain, spectral domain is shrinking. How it is interacting, you need to investigate what's the factor of this one. It's divided at here. So time domain expansion means frequency domain shrinking, but the time domain shrinking corresponds to frequency domain expansion. What about the reverse signals? It means A equals -1. In time reversal signal corresponding to frequency domain reversal. Okay, omega is a negative value. The next one is very important property. This one is duality property. It says that xt has an inverse Fourier transform expression in this way, but we just replace t with minus omega. Okay, then you know that t is just any argument for the x, but we replace t with minus omega and multiply 2 pi. This one multiplied at here. Then 2 pi times x minus omega equals xj omega times e to the minus j omega. At this moment, t is replaced by minus large capital omega. So it should be, looks like this one. Then we can replace omega with a t. Then it looks like this one. But you know that this one is inverse Fourier transform of xt. So it says that xt, take the Fourier transform, then it has a spectral domain expression j omega. Then we just replace the omega with the time variable. Then the corresponding Fourier transform are related to xt in this way: 2 pi times x minus omega minus omega is the corresponding Fourier transforms. Okay, this one is a Fourier transform of xt. So this property is called the duality. So if we have an expression for xt, then the corresponding time function has this kind of spectral properties. This one is called the duality property. Duality is quite useful, so we would like to use some of them. The first, this one shows that the time domain impulse, it's like this one, k times delta t is the time domain delta function. By taking the Fourier transform, we know that delta t is only non-zero at t equals 0. So we just replace the t equal to 0, then it's a constant k. That's the spectral domain function. So Fourier transform gives a very simple function. So we can replace xj omega with xt. At this moment, this one is xt. Okay, that's this one. Then inverse Fourier transform of this one is related to this one, but scaled by 2 pi and x, and we need to take minus signs here, but minus sign doesn't affect the delta function, so it looks like this one. Xt has a Fourier transform expression of this one. We just replaced with xt with xt. Then it's a constant value k. Then when we take the Fourier transform of this one, is related to the original time function. So it should be this expression. So we can find out the Fourier transforms of this one. So this we use the duality property. An example for the Fourier transform of a sinc function, but I replaced this note. There is some typos, so I changed this page and also this page. Just to keep in mind that there is some typo in here. We would like to take a Fourier transform of this one. So before that, let's look at here. This one is rectangular pulse. The Fourier transform has this shapes. It means rectangular pulse shape, and the time domain looks like this one, this rectangular pulse. From here, the amplitude is 1, and the time span is minus 0.5 to the minus 0.5. So 1.5 to the minus 1.5 to 1.5 to only in non-zero value. Okay, taking the Fourier transform, it shows that the sinc function. So in the spectral domain, we're taking variable as omega. In the spectral domain, it has a sinc function. So sinc function characterized by peak value and the first null. Okay, it goes like that. The peak value corresponding to area of this one is obviously 1, and the first null in omega corresponding to pi over this time difference. So 2 pi over time difference is 1. So this is 2 pi. So you can see here, this 2 pi is this one. What about this one? From time domain to the frequency domain, we call that is Fourier transform. The inverse of them is called inverse Fourier transform. Here shows that the inverse Fourier transform equations. From these equations, I just replaced this part as x. Okay. Okay, I replaced this one as x. Then dx equals d omega over 2 pi. So d omega is 2 pi of dx. So d omega can be replaced by 2 pi dx. So 2 pi and 2 pi will cancel out, and dx are shown here. And this part becomes the x. And omega is 2 pi x. So omega replaced by 2 pi x. So 2 pi x is omega. We need to take integration from minus infinity to infinity with the x variable. Then we figure out the sinc function integration pi, okay, rectangular pulse. So by use of this integration result, we can take an inverse Fourier transform of this one. Look at here. This one is a time variable, the target function. Take the Fourier transform. And here, let's take this one as x. Okay, let x is this one. Then dx are a times dt. So dt can be replaced by dx over a. dx over a is dt. So okay, this one is alpha, sorry, alpha, and this one is alpha dt. So we have to divide the alpha and dt, so dx over alpha. But we take the absolute value of this one because of if alpha is negative, then these signs will be exchanged. Okay, if negative, then minus infinity becomes infinity, and infinity becomes the net minus infinity. So we need to still exchange that one. So in minus alpha is negative value, we have to minus alpha. But alpha is positive, we can use that one. That is absolute value of alpha. So this alpha shown here, but take the absolute value of these signs. Integration range should always take minus infinity to the plus infinity, regardless of the sign of this one. That's this one. And sinc x, we replace this one as x. Then t can be replaced by x over alpha. So that's this one. T is replaced by x over alpha. So minus omega alpha corresponds to this 2 pi t. 2 pi t is this one. Then this integration look like that one. So you can see that 2 pi divided by 2 pi t is this one. So we can do the same integrations. The scaling factor a over absolute value alpha and the pi, and this should be divided by 2 pi. Then we can divide this one as 2 pi. So we have this result. This is the integration result. Another way to get the Fourier transform is using the duality. We know that the pi t is a sinc omega over 2 pi. So we know that pi t Fourier transform will give sinc omega over 2 pi. We have this result. By using this duality, we can write down that one into this way. Sinc t over 2 pi. We replace omega with the t. The Fourier transform should have 2 pi times pi rectangular plus minus omega. Okay, it should satisfy that. That one shown here. But we would like to know that the inverse Fourier transform of a times sinc alpha t. What is the Fourier transform of this function? Let's compare these two functions. The first, this scale factor just affecting the magnitude, so we can write down a times 2 pi, and to become this one alpha t, we need to time scaling factor should be 2 pi times alpha should be the scaling factor. If you time scaling over here 2 pi times alpha, then 2 pi cancel, that becomes the alpha t. So this is time scaling factor between these two functions. So time scaling factor affecting in this way, absolute value over 2 pi alpha times pi minus omega divided by 2 pi alpha. So we use the scaling factor of this property, time scaling. So look at here, we use that property. Then we can find out the Fourier transform of that one. Okay, that one shown here. So a times 2 pi over 2 pi absolute value of alpha, and we need to minus omega here, but the rectangular pulse doesn't affect it, it's minus signs because of the even function. So we can write down that one into this way. It's the same with this one. This negative sign doesn't mean in the pi, because this one is even function with respect to omega. So we have Fourier transform by use of duality. Okay. Another example for the duality, we would like to see the rectangular purse-shaped duality. First, the statement is this one. X1 is A times rectangular purse. It's okay, shown here. This one is X1. Okay, this rectangular purse, taking the Fourier transform X1 j omega are A tau sinc omega tau of 2 pi. That's this sinc function. If you're taking the Fourier transform of this time domain signal, then it shows these functions. That's this one. Okay, we can write down in several different ways, but anyway, it's these sinc functions. So first order occurred 2 pi over tau. Okay, this omega reference is 2 pi over tau. Then what about the x1t? Okay, x1t is A tau sinc omega replaced by tau t and tau over 2 pi. So we would like to take a Fourier transform of this time functions over here. Then due to the duality, the x2 Fourier transform is 2 pi times x1 minus omega. So x1 is this one, 2 pi times A tau times pi omega tau. So this should be the x2 j omega. So x1 Fourier transform has x1 j omega. The x1t should be this one. So we would like to prove that one from here. So x1t is a Fourier transform is this sinc function, A tau sinc omega tau over 2 pi. And the inverse Fourier transform are this one. So we can find out the sinc function integration should be 2 pi over tau pi t over tau. We replace the omega into omega by t. Okay. Then x1 j omega are this function. Then x2 is defined by x1t. Okay, x1t just replace the omega t. Then A tau sinc t tau over 2 pi. So by taking the inverse Fourier transform, we need to take integration of this one. So A tau is a common factor, and a sinc t tau over 2 pi e to the j omega t. Look at here to compare these two things. Then you can figure out this one is the same as this one. Okay, so we can using this result over here, 2 pi over tau pi, just change the omega with here. We need to take integration t, but at here we take integration omega. Okay, so t can be replaced by omega like that, and it gives 2 pi a omega over tau. So that's this one. So this one shows that the duality should be, this result should be come out, but we prove that it satisfies the conditions. Here is the same things. The x1t rectangular purse, take the Fourier transform, it becomes a sinc function, and we just replaced omega by t. Then time domain sinc function can be given here. Then Fourier transform of this one related to the original time domain signals. That's shown here. The amplitude is 2 pi a. Okay, here is another type error. You can see this one means that this point should be tau over 2, and this one should be minus tau over 2. Okay, this one tau minus 1 over tau. Okay, minus tau over 2 and tau over 2 is this point. So we prove that this duality property, rectangular purse, take the Fourier transform and it's replace the omega with a t, taking the Fourier transform again, then the results are related to the original time domain function, like this way. And here is okay, this one is okay, but this one is type tau over 2, and should be integration from minus tau over 2. So we just inverse Fourier transform of this one. Inverse Fourier transform of that one will give the original these functions. Okay. Here is another example by using the duality. Xt is a times cosine omega 0 t. We already know that the Fourier transform expression for xt, but we would like to find out by use of duality. Here is a two different delta function. Okay, here is time domain, and one is impulse at the tau, and another one is a minus tau. So here is two different delta function in time domain. We can take in Fourier transform by directly from here. Just integrating e to you know that e to the minus, say, omega t x t by taking integration minus infinity to the infinity dt. Think about xt is let this one delta function, then t should be minus tau, so that gives this result, and t equals to tau, then it is this one. Okay, at the t equal minus tau, it gives this one, and the t equal tau will give this one. But by adding this complex conjugate term, it becomes 2 times cosine omega tau. So we know that the two different delta function gives Fourier transform has 2 times cosine omega tau. It means that in the frequency domain, if time domain is the two different impulse, in the frequency domain, it looks like a cosine omega t, cosine omega tau. So period of this cosine omega tau is from here to here, the frequency span. So this should be 2 pi over tau. Okay. In the frequency domain, it has a sinusoidal if time domain is this one. Then by replace the t with omega 0, then this becomes 2 times, okay, here is 2 times omega replaced by t, tau, I just changed omega 0. Okay, then it becomes like that one. So tau replaced omega 0, and the t becomes the t, omega becomes the t. So it replaced in this function, and taking the Fourier transform, it should be related to this one. So 2 pi times t replaced by omega, but tau replaced by omega 0. So it looks like this one. It means that if in the time domain, if 2 cosine omega 2 cosine t omega 0, then this part should be, this one is a time domain function of this one, and amplitude is 2. This time corresponding to 2 pi over omega 0. So this is the period. So Fourier transform of this sinusoid should be a delta function of that one. In the frequency domain, okay, I would like to plot that one. In the frequency domain, it should be a delta function at the omega 0, the scaled by 2 pi. And this one is also scaled by 2 pi at the minus omega 0. Okay,